Okay, yesterday we concluded the discussion about the bidirectional DC to DC switching converter for the basically DC motor driving. I explained the two-quadrant converter, which is called the half bridge, and now I'd like to start the discussion about the four-quadrant DC to DC converter. Okay, four quadrants means that I'd like not only to have a bidirectional current, but in addition also to have a reversible voltage. Okay, so I'd like to have the possibility to get any combination in the plane of the current and the voltage at the, say, the supply port of my DC motor. In order to do that, again, I need to use the bidirectional, the two-quadrant bidirectional converter, so the switching power pole we already know. Okay, so this is the node, let's say A. This is my input capacitor to the voltage port VD, which is the input voltage that by assumption it is constant. Okay, the current here is the current IDA as usual, and the control signal commanding the status of this switch is QA. But in order, as you will know, this switching power pole with the inductance here assures the bidirectionality of the current flowing here, the current IA, but the voltage at the output between the, say, node A and N is just positive voltage. In order to make the voltage to be reversible, I have to add in parallel another switching power pole. So let me put here another B position switch this way. Let me put here the node B. This node, say, is in series with the node A because we can have here a generic load. Okay, so the same inductance that you can see in series with the node A is also in series with the node B. Okay, here we have a current IB. The voltage, let's say, between the node A and B is called V0. The node A with respect to N is the standard VA and node already analyzed for the two-quadrant converter. Then we have also VBN. Okay, so I put exactly two two-quadrant converters, two B positional switched in parallel. One is called A, and the other one is called B. This is the switch A, and then we have also the switch B. Of course, now we need two different control signal because we have QA for the switch power pole A, but then we also need another unitary switching function QB for the B switching power pole. Typically, in literature, A and B are called the legs of these four quadrant converters. Okay, so we have A leg and the leg B. So the switch in the leg A are commanded by the QA function. QB is the common signal for the switch, the leg B. So, what are our requests for the voltage? The average voltage V naught average should be reversible, so it's not required to be just positive or only negative. This voltage should be ranging from negative to positive value, okay? And typically this is a range that covers negative VD plus positive VD, okay? So this means reversibility of the voltage. Then we also need the bidirectionality of the current. So we want to maintain the basic characteristic of the two-quadrant converter. So it means that the current exiting and flowing the load should be bidirectional, okay? Is the same to say that the current ID here at the input of this four-quadrant converter should be bidirectional, okay? So we can say that ID, average value, should be, let's say, positive or negative. I naught is the current flowing through the load, okay? Is the same of the current IA. Okay, let me put in general this um, to rename the current IA just as the general current I naught, okay, which is the current flowing through the load. This is the bidirectionality. These are the two requirements. Okay, let me show you how we can get these two basic features using this four-quadrant DC-DC converter. As you will know, the average voltage at the output of the leg A, so the voltage VAN, is simply given by the duty cycle dA, so the average value of the unitary switching function QA over a period Ts multiplied the common input voltage VD. But of course, this is also true for the leg B, which is another two-quadrant switching power pole. Now the difference that the duty cycle is no more dA because the unitary switching function is different, so we can call it dB. The same happens for the current because IDA, so the current flowing into the leg A, is dA multiplied the average value of the current IA, while IDB average is dB multiplied IB. This comes from the previous analysis of the single switching power pole. If you look at the output port of this circuit, so the voltage V0 here, V0 is simply the difference between VAN and VBN. Okay, if you consider these two voltage here, V0 is derived as VAN minus VBN. And if you look at the average quantities over a period, then you can get the same expression. But now we know that this is dA multiplied VD, so we can have this expression. So the difference between the two duty cycles multiplied by the input constant voltage. Now there is a main, let's say, assumption. Let me call this the assumption. The assumption that drives all the process is that the duty cycle dB is 1 minus the duty cycle dIA. If we consider this say, relationship between the duty cycle, and it can be derived easily, that dIA minus dB is simply 2 times dA minus 1 multiplied with d. So it's like to have that V0 average value is an equivalent duty cycle multiplied with d, with the equivalent duty cycle that ranges the duty cycle ranges from 0 to 1. So if you put 0, you can get -1. If you put 1, you can get +1. So the duty cycle equivalent duty cycle now is also negative. And so that means that V naught average value effectively goes from minus VD to plus VD, negative VD to positive VD, exactly as intended. What about the current? If you look at the current is the I naught current average value is, as I said before, the same of the current IA exiting from the leg A of our circuit. And this current, if you look here, IA is exactly negative IB. Okay? By definition, this is in this way. So IDA average value is the duty cycle multiplied I naught average value, which is the same of IA, and IDB is the duty cycle dB multiplied I naught, and then you have a negative sign because IB is negative I naught. Then you have to consider this node here. So ID is the sum of IDA and IDB. And so this again is TA minus TB I naught average value, which is again this D equivalent multiplied I naught. So I naught average value, ID average value is negative I naught, positive I naught. So it's a matter of, say, considering this expression in our process that make possible this the combination in parallel of the two legs, the two switching power pole to get exactly the 4-quadrant operation. Okay, so let me just continue this discussion because I'd like to get some consideration about the control voltage we need for the correct operation of this 4-quadrant converter. Of course, we need two different control voltages now. The control voltage, let's say the control A, which is the control voltage that compared to the triangular waveform, the double edge waveform in the pulse width modulator provides the generation of QA. Okay. Then we also need a control voltage B for the leg B, for the switching power pole B, that compared to the triangular double edge waveform in the pulse width modulator provides the generation of the unitary switching function QB. So let's analyze the expression of these control voltages. Let's start with the leg A. Okay, for the leg A, we can consider the standard switching power pole. This is something that we already know because we discussed it. Okay, if you get the duty cycle versus the control voltage can range from 0 to the peak value of the triangular waveform, the carrier waveform, pulse width modulator. The duty cycle can range from 0 to 1. So here you have something that has this expression and the transfer function that is easy to derive. Here is that duty cycle control voltage A is 1 over the peak value of the triangular voltage. Okay. So let me put this expression in this form. The control A is TA multiplied V triangular waveform. Okay. And consider also this previous expression that we derived, which is, let's say, this one, that provides the relationship between the duty cycle, DIA, and the average V0 voltage. Okay, if you use this expression, V0 average value is 2 times dA minus 1 VD, then you can find that the duty cycle DIA is 1F plus V0 average value over 2 times V. Now put this DIA exactly here, and then we can find an expression for the control voltage of the leg A. Is the triangular peak value divided by 2 plus V triangular peak value divided 2 D multiplied V naught average. Okay, this is the relationship between the control voltage of the leg A and basically the output voltage V naught, the average value of the output voltage V naught. This is we can find out for the leg A, okay? But now we have to also define which is the control voltage for the leg B, okay? So what about the leg B? Here we have basically two solutions. The first one it's the solution that lead to what is called the unipolar pulse width modulation, also called three-level pulse width modulation. Which is a basic characteristic of this unipolar pulse width modulation. If you consider the leg B, let's consider for the leg B the same rule for the generation of the unitary switching function starting from a control voltage that we already used for the leg A. So for the leg A, we employed this, say, law for the generation. Remember that this law comes out from this consideration. The consideration is that we have a double-edged triangular waveform. The peak value is here, Ts is the period, and then you have a control voltage. And the unitary switching function QA is obtained by the comparison of these two, say, signals in order to get a 1 when the control voltage is higher than the triangular voltage. Okay. Of course, I also could have chosen a different law. For example, I can choose to consider QA 0 when the control voltage is higher than the triangular voltage. Okay, is a solution that has the same, say, there is no difference in that kind of, there is a selection, a choice, and I selected this law. Okay, so when the control voltage is higher than the triangular voltage, I put 1. Also, the opposite should be considered, okay? 0 instead of 1, etc. The opposite law can be also true. But in this case, the first solution, which is called unipolar pulse width modulator for the leg B, I choose the same law to generate QB starting from V control B. So what does it mean? That also in this case, I'm using a comparison that has the rule I defined before. Okay, we have B control B, a triangular waveform which period Ts. Ts is the period that I choose for my application. QB is provided in the same way. When the control voltage B is higher than the triangular waveform, then you get 1, otherwise you get 0. Okay, so what does it mean? That you can have the same, say, transfer function. Okay, the duty cycle dB versus V control B basically is the same as before. So dB is equal, sorry, dB over V control B is 1 over V triangular peak. Okay. Now, remember the basic assumption that is needed to get reversibility of the voltage, so that the duty cycle B should be 1 minus the duty cycle of the leg A. Okay. Remember also that the duty cycle A found out before is 1F plus V naught average value divided by 2. So dB is 1F minus V naught over 2 VD. This is dB, but from here I can derive the V control B, and V control B is dB multiplied V triangular peak. Okay, so using these two and putting dB here, you can find that V control B is V triangular peak divided by 2 minus multiplied V average value. Now compare this expression of the V control B, this one, okay, with the V control A expression. That is this one. As you can see that the V control B can be found simply by subtracting from the peak value of the triangular voltage the V control A. Okay, so basically I found out that V control A is V triangular peak divided by 2 plus V triangular peak 2 with the V naught and V control B can be derived by V triangular peak minus V control A of t. So these are the two control voltages for the two legs that leads to what is called the unipolar pulse width modulator. Okay, let me just consider this circuit here. Okay, what is needed for practical application? Okay, as you consider that you have two legs in parallel, okay, then you need two control voltages. So it seems that it would be required to generate two control voltages, for example, from the feedback loop or say an open loop by by inserting by the user from the external these two signals to be compared. Okay, but a more practical situation that can be easily to manage is to have just one control voltage commanding the two legs in parallel. So what I need, say practically, is to have my modulator here in which you have just one control voltage. Not A or B, just V control. And from this block, I can generate both the, not having two control voltages, okay? So this is what is typically done in application. So here what happens that you have two control voltages, okay? So we need to generate just one control voltage, but it's easy to understand that if you choose as the overall control voltage, the control voltage A, okay, of the leg A, this can be easily done. Okay, so my overall control voltage, V control, is the control voltage of the leg A. In this way, okay, this control voltage is directly connected to the leg A for the generation of the duty cycle DAA. And then you can put the same control voltage, you can subtract it from the peak value of the triangular voltage to generate the control voltage. So the control voltage for the leg B is internally generated in the modulator, starting from the control voltage of the leg A, which can be considered the overall control voltage. Okay, so for the unipolar pulse width modulator, sometimes for short I can use UPWM. Remember that sometimes calls three-level PWM. You have that V control is this one. And this is the control voltage of the leg A. The V control of the leg B is derived from the wall control voltage. Okay. I said at the beginning that this is not the unique solution. There is another solution. Okay. This is the number one unipolar pulse width modulator. The second solution is the solution that leads to the bipolar pulse width modulator. Sometimes I call these PWM, and this is also called the two-level PWM. In this case, remember my discussion about the rules by which, starting from the control voltage, I can generate the unitary switching function. In this case, the law for generating QB from a control voltage is the opposite of that of leg A. What does it mean? It means that I'm using for the leg B a rule that is like the following. Let me call this the triangular voltage, so P triangular peak here. Then we have the control voltage. How it is generated, the unitary switching function, QB. In this case, it is generated by considering that any time the control voltage V control B is higher than the triangular voltage, the unitary switching function will be 0. Otherwise, would be 1. Okay. In this situation, we have that duty cycle dB as a function of the control voltage V control B is a little bit different from before. So when the control voltage is 0, so when the control voltage is, say, here, so it's totally less than the triangular voltage, lower than triangular voltage, then you can get that the QB is always 1, so the duty cycle is 1. So we'll start from here. When the control voltage is equal to the peak value of triangular voltage, now is, say, higher than the triangular voltage, so we get 0. So you get something like this. This is now my say, graphical representation of what happens. So it means that my duty cycle dB is, let's say, 1 minus V control B over V triangular peak. And this is my transfer function for this control law, for this generation law. Okay, there is no more dB over V control B equal 1 over V triangular peak, is 1 minus that one. Okay, this is the expression for VD, for dB, sorry. Now remember that dB basic assumption is 1 minus DIA in order to get reversibility of the voltage. So we can get that dB is also 1 minus V control B over V right. Then DIA has been provided at the beginning of the discussion. DIA is a computation that we already done before here. So dB is 1 minus DIA. DIA is 1F Q plus V naught over 2VD. 1F plus V naught over 2VD. So this is 1F minus V naught over 2VD. Okay, so if you consider these two expressions, it comes out that 1F minus V naught over 2VD is the same of 1 minus V control B over V triangular peak. From this equation, we can derive V control B, which is V triangular peak value plus V triangular peak value 2 Vd multiplied V naught average. Okay, now compare this new expression for the control voltage of the leg B with the control voltage of the leg A we derived previously, which is again here. The control voltage of the leg A has the same exact expression of the control voltage of the leg B. So this quantity is equal to the control voltage of the leg A. So in this case, it's quite easy to choose as the wall control voltage commanding and generating QA and QB the control voltage A or B, which is the same. Okay, so V control voltage overall is the V control A, which is the same of the control voltage B. And this is V triangular peak divided by 2 plus 2 Vd multiplied V naught. Okay, so this happens for the bipolar pulse width modulator. So for unipolar, you have this quantity here, this definition. Okay, for the bipolar one, you get this. Okay, now let's compute the average output voltage for both the kind of modulation we derived. One is the unipolar PWM. How can you get V naught? But simply consider that this quantity here, this expression that we found out from here, for example, from this expression, from the first one, from this one, okay, we can have that V naught can be derived as a function of the control voltage, the peak value of the triangular waveform, Vd, etc. If you derive V naught from this expression, you get this result. V naught average value is the same of 2 times Vd over V triangular peak multiplied V control minus Vd. And what happens for the bipolar pulse width modulator? Again, exploits this expression here, okay, which relates the voltage V naught average value with the control voltage and with the peak value of triangular voltage and Vd. But this is basically leads to the same quantity. So in both cases that we choose unipolar pulse width modulator or bipolar pulse width modulator, the output voltage, the average value of the voltage V naught is given by the same expression, okay? Again, so we can consider this as a general solution for my four-quadrant converter for the output. We can define K, let me call this KPWM, is a constant, is 2 times VD over the peak value of the triangular waveform that are, say, constant parameters. Remember that we know that we have the K-pole, that is the constant appearing in the VAN average value expressed for the two-quadrant converter. Okay, this is 2 times K-pole, because K-pole was VD over V triangular peak. So we can say that having this gain, V naught is KPWM multiplying the control voltage minus VT. So again, for the four-quadrant converter, we get a, say, amplificator expression, okay, in which the control voltage is the input signal that is amplified by the four-quadrant converter, and the gain is KPWM. That, by the way, is the 2 times that you can find for two-quadrant converter. And then we have also an offset, is a constant voltage that translates rigidly the characteristic. Okay, so you have also the possibility to plot this gain expression in a graph, which you have V control here and V naught average value. We are considering the situation in which we are in so-called linear pulse width modulator, which the control voltage cannot be larger than peak value of the triangular voltage or can be lower than 0. Okay, this is what has been discussed so far. In that situation, what happens when the control voltage is exactly V triangular peak divided by 2? Okay, if you put here as a control voltage V triangular peak divided by 2, you get exactly 0. Okay, so here you have 0. What happens when the control voltage is the same as V triangular peak? Is VD. What happens when you have V control, which is 0? Negative VD. Okay, so this is what happens. So the output voltage is reversible, can go from negative VD to plus VD. The gain here is the KPWM, which is 2 VD over V triangular peak. Let's compare this expression with this for the four-quadrant converter. If you compare this quantity with the two quadrants converter, you get something like this. The gain is K-pole, which is 1F KPWM, and the output voltage can be only positive. Consider also the fact that if you have a control voltage which is less than V triangular peak, in the four-quadrant converter you have negative average output voltage. When the control voltage is larger than half the value of the peak, then you have positive. And when the control voltage is exactly V triangular peak value, you get 0. Okay? So basically, the leg A of this circuit is always operated as usual. So having the unitary switching function QA generated by we also did for the two-quadrant converter. Okay, so we have to compare standard control voltage with the triangular waveform, and then we generate the QA in order to have 1 when the control voltage is higher than the triangular voltage. For the leg QB, we have two choices, or to have the same rule for the generation of the QB function, or use the opposite rule. This leads to the different, say, kind of modulation. We can see what it implies, this, say, difference, when we see the waveform. So we practically see the four-quadrant converter. Okay, this is just the derivation, mathematical derivation of what happens. Okay. Are there any questions about this computation? Okay, we just divide the behavior in two different modulations depending the way we generate the QB function. So let's move to a more practical description. Okay, and so this is a description of the four-quadrant converter in real circuits, and this leads to what is called the full bridge, or, as I said by mistake yesterday, H bridge. The H bridge is the practical implementation of what I said up to now. Okay, so I have to put two switching power pole, A and B, in parallel. So again, let me put here IGBTs. These are the two switches for the leg A. So this is called TA plus, TA minus, diode A plus, diode A minus, and this is the node A. And then we have another one, which is the B leg. Here we have the load. This is the node B. Let's consider again, say, the DC motor. So this is the model of our DC motor. Back EMF, steady state condition, etc. This is called T now B plus, T B minus, D B plus, D B minus. This is the node N. Here you have V naught, and the current here is I naught. Okay. So again, this is the leg A. Leg B. Of course, we need also a modulator. The input is a generic control voltage, just one. And then I generated two unit switching functions that are QA QA, let's say, minus, QB, from which I can have also QB minus. Okay, QB minus and QA minus are connected here. So we have QA minus and QB minus. And here you have QA and QB. Okay, just single modulator, which input is the control voltage, to generate a two unitary switching function and their logical NOT version for low side switches. This is the practical implementation. So again, as we did for, say, the two quadrant converters, let's try to derive some basic waveform, okay? And let's start this analysis by considering the unipolar. PWM, okay? Let's be prepared to draw several graphs. Let's start with the basic waveforms that you can find in the modulator. So the triangular voltage, that has peak value of V. Okay, this is V triangular. And let me stress also the value at half the peak value, which is here. Okay. Then we need the control voltage, the overall control voltage. The overall control voltage is the control voltage that drives the operation of the leg A. This is always happen, both for unipolar and bipolar pulse width modulator. So let's suppose that this is the control voltage T, okay, which is the control voltage for the leg A. So this means that I can use these two waveforms, compare these two waveforms in the modulator to find out which is QA standard generation low. So when the control voltage is higher, it is 1. Otherwise, 0. This is TS. Okay, so TS is in between here, TS. What happens? What about the unity switching function QB? To derive QB, we need to know which is the control voltage of the leg B. So now we have to remember in which way the control voltage of the leg B can be generated, can be derived from the overall control voltage. Okay, so let me just go here. The control voltage of the leg B is generated by this computation, the peak value of the triangular voltage minus the control voltage. This is the control voltage, the blue one. The peak value is this. If you do this computation, you find out this value here. You always get a control voltage for the leg B, which is the symmetric version with respect to the V triangular half value of the control voltage A. Okay, this is the symmetrical with respect to 1F V triangular peak value. Now we have a control voltage for the leg B, we have a triangular waveform, we have to use the same rule of generation for the QB that we use for the leg A. So when the triangular waveform is less than the control voltage, the QB is 1. Okay? Otherwise, it would be 0. Okay? I employ the same exact generation rule for QB starting from V control B. Now what happens that in which way I can obtain, for example, the voltage V naught. V naught is V A, let's say N minus V Bn. Okay, and VAN instantaneous value is QA VD minus QB VD. So you have to simply multiply it by VD the two unitary switching, the difference between the two unitary switching functions. And so that means that you have here 0, because you have the same level in this interval. Then you have something which is higher as VD. Then you can get both 0, so the result, the difference is 0. Then you have the difference which is positive, 0, positive, 0, positive, etc. This is V naught, instantaneous value, okay? Which is the average value of this quantity, but the average value is something that is here. Okay? V naught is positive, according to this construction. It is something that surprising us or not. But since what I said here is that when the control voltage here is larger than half the value of the triangular waveform peak, then the average value of the V naught waveform must be positive. And this is exactly the case I say draw here. My control voltage, the blue curve here, is larger than the peak value, half the peak value of the triangular waveform. So I'm expecting then the output voltage V naught should be positive. Another consideration, which is the width of these pulse. This interval here, from this point to this other point, is Ts. Okay, this is Ts. This quantity is simply the, say, the T-on interval. Okay, so this quantity here is duty cycle dA multiplied Ts. What is the time interval here? But is dB multiplied Ts. So which is the time interval you have here? Is the difference between these two pulses. Basic is half the difference between the two. So it is dA minus dB divided by 2 multiplied Ts. all these quantity, all these pulses have this expression. Okay. It's easy to see in this graph. Basically, my graph is not exactly, say, because maybe I is not so too much. It's not precise. Okay, but anyway, if you look, you can see that dB is exactly 1 minus DIA. You have to consider the same period here, and the same period you can see that there is exactly this relationship which holds, which is exactly my position at the beginning of the discussion. The constraints that I have to respect in order to have the reversibility of the voltage. Okay? This happens, this is just by construction, since I derived this modulation here, comes in this way. So this simply confirm what I am, say, derived previously mathematically. Okay, what happens about the output voltage? See what happens. My switching frequency is Ts. Okay, Ts is the period of the triangular waveform and the period of the rectangular waveform for the unitary switching function. But at the output, I see that my repetition period is twice the switching frequency. So V naught as frequency, which is 2 times Fs. Is it important? Is not important? Of course, we have to say that look, for example, think about the output spectrum of the voltage V naught. Okay, if you look at the output spectrum, you can see that now you have an average value. This average value is K, P, W, M, P control minus Pd. Okay. Then you have harmonics, and then you have fundamentals. And which is the fundamental? The fundamental is not at Fs, but is at 2Fs. And then the harmonics are integers multiply of this fundamental at 2Fs. So you have, for example, 4Fs. Oh, I cannot change the, okay. 4Fs, 6Fs, etc. So with respect to the spectrum that you can have for output voltage, like the VAN in the two-quadrant converter that switches at the same frequency Fs. Now the spectrum has an harmonic content which is, say, less, because the harmonics are, say, the spread between the harmonics is, say, 2Fs and not Fs. This, of course, helps us in relaxing the specification of the demodulator at the output of this circuit. So the filter, the low-pass filter that you need in order to extract the DC value from this rectangular, highly distorted waveform can be relaxed, because now the first harmonic line that the filter have to, say, reduce, have to attenuate, is at frequency 2Fs and not Fs. So my filters can be a filter that can have a pole, let's say, at higher frequency than before. For example, this can be my filter demodulator. Transfer function. So this also means that I'm expecting from this solution an amplitude of the peak-to-peak ripple of the output current I naught, which can be reduced, okay? Because now the filtering action, having the same filter, this filtering solution is more effective than the same filter applied to a waveform that has a frequency of fs, okay? So this can be, for sure, an advantage. Okay, this happens for a unipolar voltage, unipolar pulse width modulator, having the control voltage higher than the V triangular peak divided by 2. See what happens when you have the same unipolar, so also unipolar PWM as before. Okay, but now consider what happens when I have a control voltage which is less than V triangular peak divided by 2. Supposing that now my control voltage is here. This is V control, which, by the way, is also the control of the leg A. Okay, so let's start with QA. Standard classical rule for generation QA from V control A, and we get this waveform. Okay. Now, what happens for the control voltage of the leg B? As you can see, for unipolar, you should remember that for the unipolar PWM, the control voltage for the leg B is V triangular peak minus V control. So, as we did before, it happens that the control voltage for the leg B is the symmetric position of the V control with respect to F, the peak value of the triangular voltage. Now we can generate QB, and QB is obtained by the standard generation law. Okay. Now V naught is the difference between the two functions multiplied by Vd. So you get here 0. Then you have negative Vt, 0, negative Vt, and 0, negative Vt, 0, etc. Okay? Which is the average value? I don't know, maybe here. It is negative. It comes out, it's no surprise, because the control voltage here is less than the triangular peak. And so the average voltage should be negative. Always the same consideration that we had before now are also true. So it means that this time interval again is, say, DIATS. This is DBTS. So the difference between the two now, it comes to be exactly as before. And the switching frequency of the output is, let's say, twice the switching frequency. So it can help to reduce, say, to enhance the filtering effect of the demodulator. So in this case, I can use the filter provided by the motor itself, by the inductance and the resistance, for example. Another consideration that now appears to be, say, clear is why this kind of modulation is called unipolar or three levels modulation. Okay, unipolar because look at what happens here when we have the positive average voltage. Okay, the voltage you can get at the output, the instantaneous voltage V naught here, is larger than zero, is totally positive or zero. Okay, is, say, V naught T is always greater than zero. If you consider what happens here, where the control voltage is less than V triangular peak value divided by 2, V naught is, say, less than zero. The instantaneous value is always zero. So there is no situation, there is no possibility to have in the waveform V naught over T simultaneously positive or negative value. Okay, you can have also only positive value or negative value. Okay, positive value when the control voltage is higher than half the value of the peak triangular waveform, or negative value when the control voltage is less than this value. Means that the waveform is unipolar. A bipolar waveform is a waveform that can have positive or negative value in a period. But here this not happens. So is a unipolar pulse width modulator for this reason. Why it is called also three-level PWM? Because the value that can be reached by the output voltage V naught are exactly three. You have plus VD, here, 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 zero, here, here, or here, and negative VD. So plus VD, zero, negative VD. This is the reason why you get this name. Questions, doubts, problems, issues, whatever you can have, problems. Okay, guys, if you have no question, I would like to stop here before, say, starting to draw other several graphs, okay? And next week, we can continue this unipolar pulse width modulator and then move to the bipolar pulse width modulator and then continue on this topic, okay? If you have no question, I can, I would like to stop here, okay? Okay, guys, thank you very much. Have a nice day, nice weekend. See you.